Okay. So last time I did many examples of optimization problems last time, and in the second half of the course we discussed the second derivative test. Instead of doing the slope chart, we can differentiate the function twice, and for some critical values. So there are two families of critical values. First, you have to make sure that the function is defined at this value, and the two families are, well, f prime is 0 or f prime is undefined. And we saw last time that if you have a critical value for which f prime is equal to 0, then you can compute f prime prime, the second derivative, plug your critical value in, and then the sign tells you if it's a max or a min. So if f prime prime of a, say, is positive, then when things are positive you smile, so it gives you a minimum in your face, and if things are negative then you groan, so you have now a maximum. And so I just want to do one more example of optimization, and after we'll start talking about the multivariable situation. So there's something else I wanted to say. Yeah, I guess not that I want you to drop, but today is the last day to withdraw with permission, just in case you want to drop my course or another course. You know it's today. And as I said, so after today we'll have a good idea of how many students there are, and then I can update the room we will use for the final exam. Okay, so an extra example. There is a similar, not quite the same, but there is a similar example or a similar problem in your assignment that is due on Wednesday. There is also a new assignment now available. I think you will have, well, I don't know if it's a break, but I think that the last assignments have been difficult, and today's assignment I think is easier. Good for you. But don't wait until Monday morning next week to start working on it anyway, but I think you will have a kind of relief. Okay, so an open top box with a rectangular base twice as long as wide. And with a volume of 36 feet cubed is to be constructed. Again, I took this question in an American book because it's in feet. Is to be constructed. Very good. Find the dimensions of the box, minimizing the amount of material used. So in the assignment that is due on Wednesday, I think it's assignment 7, there's also a box. It's constructed a bit differently, so maybe just a word about the question that you have in your assignment. It's not really related to, well, it is partially related to that. In the assignment, you start with a rectangular piece like that, and you cut off some corner. Well, actually, you cut off the 4 corners. So that gives you 4 sides that you can fold. So if you fold along these lines, so you will get a box, right? So now, I mean, erase these things here because you cut them off, and then you fold the sides, so you would get a box. Okay? So that's the idea in the assignment. It's not exactly the same thing here. So we're not told how to build up the box. We just know that we need to have such a box. Okay, so let me erase this. It's not related to the current problem. Okay, so we want to build up a box, so it will look like maybe something like that. Okay. And so I know what the volume of the box is, so maybe I can introduce some variables. So I have, say, x here, y is the height, and okay, so if x is the width or the depth of my box, I guess I can put z here if I want for the length, but if I read the text, I know that the length is twice as long, is twice as large or long as the width. So I don't really need to put 2z, but 2x, okay? Just because it is twice as long as wide. So, okay, now we have to minimize the amount of material used. So we have to minimize the amount of material. So actually the sum of the areas of the sides. Sorry, it doesn't look, it's not rectangular. Anyway, it is supposed to be. So we have to minimize the sum of the areas of the sides, the four sides, and the bottom, because it is an open top box. Okay, so there is no cover, so we don't consider this part. So what is the area of this side here? Well, it is x times y. I guess I forgot to do one thing important. I forgot to introduce the variables. So let's say x be the width of the box and y be its height. And as we said from the text, we know that the length is now 2x. Okay, so now we have to minimize the amount of material used. So as I said, we have to add the areas of all sides plus the bottom, the base. So the area of this side, I mean, that's supposed to be a rectangle. So this is xy. There is another side on the left here, which is, well, exactly the same as this one. So we have twice xy. And the area of the front side here, well, the height is still y, and the length is 2x, so plus 2xy. And of course, we have the same thing at the back, so plus 2xy. So these are for the four sides. Let's say I call this sum A for area. And then I need to add the area of the base. So the base is 2x times x, so 2x squared. Okay? So now we have A expressed in terms of x and y. And if I simplify this, I get just 6xy plus 2x squared. So this is my total area. And now I have to minimize this, so I have to express A in terms of one variable only. So we should have another piece of information, and it is here. The volume is 36, and we should be able to use this in order to express y in terms of x or x in terms of y. So we have to minimize this quantity subject to a volume of, well, what is the volume of that box? Length times width times height. So 2x times y. So this is my volume, and the volume is supposed to be 36. So I have 2x squared y. This is 36. Now it's easy to isolate y in here. Just divide by 2x squared on both sides. So we get y is equal to 36 divided by 2x squared, or if you prefer, 18 over x squared. And now I can rewrite my area A in terms of x only. Yes?
Where did you get 2x squared y?
It's the volume of a box. The volume of a box is the length, 2x, times the width, x, so I get my 2x squared, times the height, y. Okay? And then I get this, I just divide by 2x squared on both sides. So we have to minimize a, which is this here, but I will replace y by that expression. So I have 6x times 18 over x squared plus 2x squared. Observe also that for my box to exist, I certainly need my x and y to be both larger than 0. So it's not a problem here if I divide by x, because x is not going to be 0. And furthermore, I can simplify the x because it's not 0. So here I get 108. This is 6 times 18 over x plus 2x squared. Okay? Okay, so this is the function I have to minimize. Now maybe I can write a of x because now it depends on x only. So now I have to compute f prime, find the critical values, maybe do a slope chart, or because here I want to illustrate one more time the second derivative test, that's what I'm going to do. Okay, so we have that a prime is equal to, so the derivative of a with respect to x. Again, I can see, I guess, this as 108x to the negative 1. Actually, that's the way I like to see it, but you can do a quotient rule also if you want. But I prefer to see it in this way. So if I differentiate, then I drop the negative in front. I get negative 108x to the negative 2 that I can rewrite as a fraction after. So you get negative 108 over x squared. As I said, you can also use the quotient rule. It would be derivative of this number, which is 0 times x, minus the number times 1. So just minus 108 over the denominator squared. So you would get the same answer, plus 4x. Okay, so this is the derivative. And now for the critical values, there are two kinds of critical values. This for which a prime is 0, this for which a prime is undefined. But again, it is always nice to have in mind the domain of the original function. So the domain of ax is, well, now here. And we said that x must be greater than 0, so maybe I forgot to write it here. For the problem to make sense, I mean, x is the width of the box, so it must be positive, strictly positive. So the domain of ax is, say, from 0 to infinity. And now I compute, well, I find my critical values. So when do we have a prime equal to 0? A prime is equal to 0 if and only if this is equal to 0. Minus 108 over x squared plus 4x is equal to 0. If and only if, maybe I take this guy which is negative and I send it on the right hand side, like this. And then I can multiply by x squared and then divide by 4. So I get x cubed is equal to 108 over 4, which is 27. So I get x cubed, is equal to 27. And then you take the third root on both sides and you get x is equal to 3. Okay? By taking the third root on both sides. So you get 3. So this is one critical value because, of course, it falls in the domain of the original function. Now, the other family of critical values, a prime x, which is equal to negative 108 over x squared plus 4x. This, well, it would be undefined only when x takes the value 0, but 0 is not in the domain of A. So I guess I can say that this one is defined for all x in the domain of A. So the only critical value we found is 3. So the only critical value is x is equal to 3. This example is in feet, so let's say 3 feet. And now this is very likely our well, the solution we're looking for, but we have to make sure. So at the final exam, for instance, make sure to do a slope chart or the second derivative test. Verify that your answer is indeed a max or min. So here, if I want to apply the second derivative test, that's the purpose of that example. I compute A prime prime. Maybe I can rewrite A prime for a moment. Again, in the form that I like to see it when it comes time to differentiate. So A prime prime, if I drop the negative 2 in front, I will get 216 x to the negative 3, so like this, plus 4. This is my second derivative. And then I plug 3 in. And I'm just interested in the sign of that. So since A prime prime of 3 is 216 over 3 cubed plus 4, I don't know what this gives, but I know the sign of that clearly, right? 216 divided by something positive is positive, plus 4 is positive. Okay, so I don't really care about the exact value. I just know it's positive. So I know that this guy is a relative min. Is a relative minimum. And for the moment, I just know that it is a relative and not necessarily absolute. But if you read again what we discussed in class when I introduced the second derivative test, there was a moreover part. The moreover part was if the function is continuous and the number you found is the unique extremum, then it's also an absolute one. So because or since AX is continuous on 0 infinity, and 3 is the unique extremum on that interval, then it is also an absolute one. And x is equal to 3 is also an absolute min. Okay, are we done with the question? We read the question again. Find the dimensions of the box. So no, I just have its width for the moment. So the dimensions must be well, the width is x, so 3 feet. The length, this was 2x, so 6 feet. And the height, this was our y. And y, is it still on the board?
18 over x squared.
Thank you. 18 over x squared, you told me?
Yep.
Yeah, okay, thanks. So 18 over 9, so 2 feet. Okay? You can verify that the volume is going to be 36. 3 times 6 is 18, times 2 is 36. I guess it's harder to verify that the material is minimized, the quantity of material is minimized, but at least the volume is correct. Many questions? Good. Okay. So I'm done with this portion of the course, which is optimization in one variable. And we're going to start the last, well, maybe I should not say the last, but there is a topic that I certainly want to cover, which is multivariable calculus. The other one, which is introduction to integration. It depends if I have time. Normally I have time to discuss this a bit. Okay, so chapter 17, sorry. Multivariable calculus. And I'm a bit disorganized because I start my chapter 17 with section 2.8. Strange, but in a previous edition of the book, section 2.8 was section 17.1. Now it's not, but so 2.8 is introduction to multivariable functions. Okay, so well, I guess just a reminder. I'm not sure it's super useful. But so far, we discussed optimizations of functions in one variable. So we have optimized functions in one variable, say y is equal to f of x. And what are the steps? I guess I just shown an example of what are the steps. So first, maybe find, or let's say given f of x, because sometimes we have to construct f of x a bit. Okay, so find f prime. Then we find the critical values. And 3, we test them with a slope chart that is called the first derivative test. Or with the second derivative test that I just illustrated. A bit small, I hope we can see this on the camera. Okay, and the idea will be to, I guess, mimic this, but in the 2 or 3 or 4 variable situation. Actually, the beginning of the theory will be about n variable situation, but we will only see how to optimize in the case of 2 variables. Okay, of course, some functions depend on several variables. So actually, I'm not sure I should write this down, but let's say in a general, if there's no restriction on the variables, normally we can see, in the one variable case, we can see a function as you choose one input number, let's say an R normally, and so you take one input number, you put it in the magic box, which is your function, and then you get an output number, right? So it is like you put one number here and you get one number at the end. And if it depends on several variables, then it means that you might need to put n variables inside your function to get one output number at the end. Okay, so it's the idea of functions in several variables. I have examples. So first, do you remember the compound interest formula? S is equal to P times 1 plus R to the power N. Well, there is a P, there is an R, and there is an N. So S depends on these three numbers, right? So one can see the compound amount formula. So let's say S of P of R and of N, which is P 1 plus R to the power N, has a function in three variables. Has a function in three variables. So namely P, R, and N. So you need to know these three quantities to compute S. Okay? And you just plug them in that formula. An example of that example, or say for instance, and I guess the order of the variables here is important, so I put my P in first place. So if I write S of 100, 0.05, and say 6, well, P takes the value 100, R takes the value 0.05, and N takes the value 6. Okay, so the order is important here. So it would be, well, just replace P is 100, R, so 1 plus 0.05, and N is 6, we said. Okay, so just that. So actually it's the formula that we need if we want to know what is the compound amount when we invest $100 at 5% during 6 years. And if you compute that, you would get 134 and 1 cent. Okay? So as you see, I need three numbers. I need three variables to define one number, one variable. This is one example. Another that I will partially give to you is actually an example that we should be able to solve and that we will solve together eventually, but I need to give you a bit of theory before finishing my example 2. It is an example that was in my final exam, well, already some years ago now, in 2011. And it goes as follows. The company is developing a new soft drink. Period. The cost in dollars to produce a batch. So a batch is a vague word for a certain quantity of drink. Is, let's say C. My total cost would depend on two quantities, n, x, y. And the formula is 2,200 plus 27x cubed minus 72xy plus 8y squared. We don't really know how they got that formula. I guess I need to tell you what x and y are. So where x is the number of kilograms of sugar per batch. And Y is the number of kilograms of flavoring per batch. Okay, so for instance, if I choose a certain amount of kilograms of sugar, then I replace X by that amount of sugar and Y by the amount of flavoring per batch, so that's relatively easy. Okay, so I guess I can maybe complete partially that example. For instance, if I replace, I guess my for instance would have been better here. If I want to compute C5 of 2, it means I replace X by 5 and Y by 2. So I get 2,200 plus 27 X cubed, but X is 5, so 5 cubed, minus 72 times 5 times 2 plus 8 times 2 squared, because this is 8y squared. And if you add all this, you get $4,887. If I compute C2 of 5, should I get the same answer? No, because, well, it's a completely different thing. X takes the value 2, Y takes the value 5 now. So maybe I can do it again. 2,200 plus 27, 2 cubed, minus 72 times 2 times 5, plus 8 times 5 squared. It's indeed different. It is 1,886. It's a big difference. And let's say I put no sugar and no flavor and 0, 0. Just 20, yeah, just 2,200. Okay. So it costs less actually to put things in. It's maybe a strange example, I don't know. But I mean, often they replace sugar by aspartame, for instance. So it's not because they don't put sugar that it costs nothing. Clearly, it costs more. Of course, if these three options were the only options we have, if the objective is to minimize the total cost, we would choose, I guess, this option here, X is 2 and Y is 5. Okay, but this is not what we will have to do. The question that we cannot answer now is, of course, find X and Y so that the cost is minimized. Okay, so let's say a question that we will eventually be able to answer. Find X and Y both greater than or equal to 0 because are quantities that minimize the cost function Cxy. And the answer, well, later. Okay, so I will come back on that example eventually. Okay. So that's roughly what that's roughly what is the objective of that chapter discussion. It will be to optimize two variables functions. But I will explain the theory for n variables. For the optimization itself, we'll just look at the two variable situation. Okay, any questions on that so far? Okay, so in general, an n variable function looks like, it's a y that depends on the n variables. So often we give indices subscript to the variables, so there are n of them. Like in my compound amount formula, there were 3 of them. What could be the domain of such a function? How do you think we extend the definition of domain? Well, in the one variable situation, what is the domain? It's all the x values, say, that we can assign, that we can choose, so that when I plug x in the formula, I do get a result at the end. So it's exactly the same thing. So the domain will consist of all, well, I guess it's not a pair, it's not a triple, it's an n tuple of values, one for each variable, so that if I replace these variables by these values, then I get a number at the end. So the domain of such a function consists of all, well, we call this n tuple, like a 2 tuple is a pair, a 3 tuple is a triple, but n tuple in general. So n of all n tuples. Let's say x1, x2 up to xn, which is equal to, I don't know, s1, s2 up to sn, such that, okay, let's say for which f of s1, s2 up to sn exists. And especially like in my example that I gave, x and y were quantities, so they could not be negative. So if there is a context to the function, we have to make sure that these quantities or these values make sense. So for which exist and say the n tuple makes sense in the context of the problem, if there is a context. And the range normally is all, say, the y's that we can get. It's exactly the same thing again. So you have to see a multiple variable function as, maybe I'm using words that you don't really know now, but a map or, well, okay, let's say just a function. I guess that's a better word. From Rn to R, as I said, you need n variables to obtain one number. So the range, again, is all the y's that we can get. So the range consists of all output numbers, or let's say y values in this context, that we can get, or that we can obtain by assigning values to our variables. By assigning, or let's say as x1, x2 up to xn runs through the domain. Okay, so it's roughly the same definition as in the one variable case, it's just that now there are more than one variable. And in the example that I just erased, actually the cost of producing a batch, as I said, well, so the domain would be all pairs x, y, where both x and y are positive, or I should say non-negative, because they could be 0. Okay, so that would be the domain, and the range, we don't really know what kind of numbers we can get. It's not really easy to compute. So an example, let's say if y is equal to the function in 4 variables, x1, x2, x3, x4, and let's say it's given by x1 times x2 times x3 minus x4 over x1 minus x3. Let's say then what is, I don't know what, f of 0, 1, 3, 2, for instance. Well, I replace x1 by 0, x2 by 1, x3 by 3, x4 by 2. I get 0 times 1 times 3 minus 2 over 0 minus 3. It would be just 2/3. Okay, that's pretty simple. Just assign values to the variables. And again, the order is important. So this is the value for x1, x2, x3, and x4. What is the domain of f? What's the domain of f?
x1 minus x3 can't equal 0.
Exactly, because we don't want to divide by 0. So I guess if I use the set builder notation, it will be all the 4 tuple x1, x2, x3, and x4, such that, as you said, x1 minus x3 must be different from 0. So maybe I just say, okay, x1 must be different from x3, which is the equivalent to what you said. That's the domain. And what's the range here? I guess that's a harder question, not the question I would ask you in an exam. But do you have an idea of what the range could be?
They can be infinity to 0 and then 0 to infinity.
Actually, it's all real numbers. You can get 0, yeah. Okay, how to see that? I mean, if x1 is 0, for instance, okay? If x1 is 0, that's a product. So this dies, and this also dies. So we just have minus x4 over minus x3. And if x3 is negative 1, then it's negative negative 1. So it's divided by 1, actually. So we just have negative x4 in that case. So clearly we can, I mean, if I need to have a certain real number, I just have to assign to x4 the negative of that number. So here, in this specific example, the ranges are, because it was not too difficult to figure it out on that example. But as I said, it's not really part of that course. I'm not really going to test you on that kind of question. The domain, yes, that's something that you should be able to understand, but the range in general is quite difficult to find. Okay, now we'll discuss geometric interpretation of a two-variable function. So geometric representation or interpretation. Just for the two-variable functions. But let's start with something we know well. I hope you know well. The one-variable case. So in that case, we have y, which is f of x. Okay? And if I don't know if geometric tells you, well, it is really clear about what I want to discuss here. But like, okay, maybe I read it. if you have a function like this, well, you have an x-axis and a y-axis. And if I draw all the points, if I plot all the points that live on that, well, that satisfy this, then we get a curve. Okay? I don't know how it looks like. Okay, so in the one variable situation, we get the curve. This yields a curve in the xy plane, or into two-dimensional space. What will I get if now I have two variables? So y depends on x1, x2, or maybe because I just have two variables, I will use x, y, z. So if I have z, which is a function of x and y, for instance. Well, if I play roughly the same game as there, here I had two axes, so here I would need three axes. So maybe like that, and like that. See, I will try to draw in 3 dimensions a bit. I don't know exactly why, but the convention in math is that we put the x-axis here, the y-axis there, and the z-axis here. So what kind of object could I get if I plot all the points? What does that mean exactly? It means that I choose, well, I assign a certain value to x. Well, okay, like here, you choose a certain value x0, you plug it here in the formula, you compute it, and you have a y value y0, so you have a point x0, y0, and if you draw all your points, then you get the curve, okay? What do we get if we do the same thing here? So I assign a value to x, let's say x0, and assign a value to y, y0, and I get, so in the xy plane that you have here, there's a point x0, y0 if you want. And then I plug this point in the formula to get a z value. So I would get, say, z0, which is maybe here. So I get something like a point like that, which is, say, the point x0, y0, z0. So it's a kind of point floating, right, over the xy plane. And if I do that for all the possible, well, I mean, if I let xy run through the domain, then the x0 might move, y0 might move, I get a bunch of points, and I plot all my points floating, and I get, what do I get?
A surface, something?
A surface, yeah, that's a word I was looking for, thanks. Okay, so we get the surface, so maybe we have, I don't know, it's not going to look nice. We have maybe, okay, it looks more like a fish than a surface, but, and of course it's hard to draw because the domain might be infinite in all the directions, so it's a kind of surface or a kind of blanket which is infinite maybe. Actually it lives over the domain of the function. So if the domain is, say, a little portion here, you will just have your surface living over that surface, but in general it is like an infinite blanket, and you don't seem to understand what I drew.
Not sure.
It's not, you're not sure. Okay, like look outside, you see some valleys and some mountains and whatever, okay? So let's assume the planet is flat. Okay, so the planet is flat. And then you choose, say, some, I don't know, a position, x, y, and then z is the altitude, right? So it's exactly that, okay? So the planet is the XY plane here, and then you choose a point, and then you get the altitude. So you get mountains and you get valleys and things like that, okay? So it's what you see when you look outside. It looks like a big surface. Okay, that's what I tried to draw. So we get a surface, and of course this Z0, I guess you understood it, but Y0, sorry, is f of x0, y0. So you put the x0 and y0 in the formula and you get z0. So okay, so each pair x0, y0 in the domain of the function gives rise to a point x0, y0, z0, which is f of x0, y0, that floats in the 3D space. And if you draw them all, then you get a surface. So altogether, they form a surface which is generally, I guess this parenthesis should have been before the word surface, but the surface is generally infinite if the domain is infinite, or if the domain, say, consists of all the x and y that are in between 0 and 1, then you just get a square, and then you will have just a piece of a surface over the square 1, 1. But in general, it is infinite. Lying or floating over the domain of F. Okay, so let's start to draw clearly. Maybe just a reminder about Mat 196. When you discussed systems of linear equations in several variables, for instance, when we have to solve a system of linear equations in 3 variables, if you remember correctly, I guess, well, that's what I say. I don't know what the other professors explained, but it consists of planes, and we're trying to find the point of intersections of planes. So a plane is a specific example of a surface. So if you have a linear equation in 3 variable x, y, z, then you get, and you try to draw this, and you get the plane. So it's a kind of surface, as I said. But here, in general, we get something which is not as straight as a plane. It looks like a blanket, or I don't know. Maybe just a note that, well, I guess you can write it in your notes, but I'm not going to insist at all on this. It's just that I will have some statements that will refer to continuous multivariable functions. So I want to very vaguely define what continuous means here. So a function y that depends on n variables is said to be continuous at a point a1, a2, up to an if, and I need to use the limit notation that I very vaguely explained. So when x1 approaches the value a1, when x2 approaches the value a2, and when xn approaches the value an, and you replace your x's in your function, then the number that you're supposed to approach, if it's continuous, it is the number f of a1, a2 up to an. Which seems, I guess, quite natural that if x1 is quite close from a1 and x2 is quite close from a2 and so on, and then you replace in here, you will get something which is quite close to that. It's not always the case. In particular, maybe just to give you an idea of what is a continuous two-variable function, a continuous two-variable function or the geometric representation of a two-variable function. We said it's a surface, but it would be an unbroken surface. So with no holes or things like that. Okay, so when we discuss the one variable, well, actually it's not the first time I put the word continuous on the board. I also put it when we discussed the one variable situation, and in the one variable situation it was an unbroken curve. So it's a bit the same idea here. It is an unbroken surface, so there is no hole or like jumps anywhere. Okay, so as I said, you will see the word continuous at some places. That's what it means, but I will not ask you to verify that the function is continuous. And I guess we're done with 2.8, unless you have questions. Good? So in the new assignments, well, there are 10 questions, and I think the first 3 are about 2.8. Roughly, it is just, plug numbers in a multivariable function. Okay, so let's start 17.1, partial derivatives. Okay, so I will start again in a two-variable situation for simplicity, but it works in every dimension with any number of variables. It's just that in the two-variable case I have, even if I'm bad to draw surfaces, I have this visual support. So that's why I'm going to start with the two-variable situation. So suppose that z is a function of x and y. And, okay, so its geometric representation is a surface. And we look at this surface. When y takes a fixed value, say b. So what do we get? Again, I will try to draw something. If you have the textbook, there are better pictures than what I'm able to do. So you have your surface. And you have, let me draw it behind, you have your 3 axes. So x here, y here, and z here. And as I said, you fix a value for y. So you have, say, b. Let's say b is here, and you fix it. That means that all the pairs x, y that you put in your function are all of the form x, b. Okay? Y always takes the value b, say. So you get, for instance, if you give a certain value a to this x, then you have the point, AB here that you can put in your function f, and then you get a point on your surface, which is the point a, b, f of ab. Right? And I said y is fixed. So let's say x varies. What kind of... my question won't be clear. I will just tell you what the answer is. I get a kind of path on your on the surface, okay, or a curve on the surface. So if you fix y is equal to b and you let x take different values, you will get points that they are all kind of aligned and live over this line there. So actually all the points here, when you move them up, they form a curve on the surface. Okay? Is this clear? No? Do you have a precise question for me? Or
Understand how what the line above it means?
Okay. This one?
Yeah.
Okay. Okay. So actually, I'm saying that if you have a value a0, for instance, and you have whatever. Okay, so you have this point that corresponds to A, and then if you choose a prime, maybe a prime here, then you will have another point, whoops, supposed to be horizontal. You will have another point, say, here, which is a prime b, and then if you move it up, you will maybe be here instead. Okay, so you will have, say, the point here, a prime. Prime is not for derivative, it's just a notation. A prime b, f of a prime b. And if you take all the possible values for x here, you will get a bunch of points and they all live on the same curve. Okay, so they form a curve that lives on the surface. And I just drew a part of the surface. As I said, normally this surface is infinite. Okay, so you have a curve on that surface. And the title of the section is Partial Derivatives. So now, if you fix y is always equal to b, say, then this curve depends only on x, not on y anymore, because y is fixed to b. So this curve here is given by, was the representation of f of xb. So let me write this down. Then z, which is f of xb, if y is fixed, defines or determines a curve on the surface fxy, and in particular f of xb is now a one variable function. It depends just on x. So is a one variable function. Actually, I will be honest with you. I try to tell you a long story now. I hope you will understand it. But when will come time to really compute partial derivatives, it will be relatively easy. but I try to explain you what is behind the computation of partial derivatives. Okay, so now maybe I erase this a prime b because it's not just, well, at the right place, I should say. Okay, so now let's say you are standing here. Let's draw somebody here. Okay, it's somebody there. And the person wants to walk on that curve. And of course, well, maybe not of course, but the person wants to know how steep it is. Okay, in the direction indicated by that curve. So you walk on the curve, and is it going up? Is it going down? So that's the idea of partial derivatives, because we want to know what is the slope in one specific direction. We don't look at the big picture, but just at this curve. So that's what we will do now. So one can differentiate f of xb with respect to x. With respect to x, to find the instantaneous rate of change, or let's just say the slope, of the tangent line at any point a, b, f of ab. So maybe I would try to draw the tangent line. Or maybe what I said is maybe more important than what I wrote. You really want to know what is the slope in the direction indicated by the curve. So let's say here my tangent line could be, let's say, like that. Okay? But with the perspective, it's maybe hard to say if it's going up or down. It seems to go up here, but okay. So actually, for a moment, you can forget that you are in a 3D space. The y dimension does not exist anymore because y is fixed. So you just have your x and z axis that really counts. So this curve here can be seen as a function z in terms of x. And then I guess the x-axis increases in this way. So if I go in this direction, I would like to know if it's going up or down. Okay, so that's the idea behind partial derivatives. The slope is called the partial derivative of f with respect to x at AB. B is fixed, and how do we get again the slope of the tangent line? We let x vary just a little bit. I mean, it was do you remember what was the definition of the instantaneous rate of change or the derivative? There was a limit as h approaches 0, f of x plus h minus f of x over h. So we let the distance between the 2 points be as small as possible. So it's exactly the same idea here. Once that y is fixed, you take, say, several points on your curve and with a distance smaller and smaller and smaller, and then you compute the slope of the secant lines, and the limiting value is the slope of the tangent line. That's exactly the same idea. And so in the one variable case, we had the prime notation. But here, if I write f prime, it's not really precise because I don't know if prime refers to x or y. So it's not the same notation as in the one variable case. Instead of prime, we write f index or subscript x ab. And mathematically, the formal definition is exactly what I just said, but adapted to the situation in which we are. The limit as h approaches 0 of f of a plus h b, because y is fixed, minus f of ab over h. So it's exactly the same definition as in the one variable situation, but adapted to the two variable situation. So y is fixed, y is always b, and we let, say, x vary a little bit. We start at the point AB, and we increase or decrease a by h, because, I mean, h is not necessarily positive. It could be negative as well. So we just have a very little increment or decrement. Is that the correct word? Decrement? Increment, say. And then, so this is the rise over run. Okay, it's the same idea as usual. Okay, so, and it represents, as I said, the slope of the tangent line, but I guess more, what we will maybe understand a bit more, it represents the slope of f of x at the point okay, as I said, you're standing on the surface at the point AB f of b. So at the point AB f of AB, and you want to walk on the curve. So you want to walk in a direction that is actually parallel to the x-axis, because the the y value is fixed, and then you just move this point here, so you walk on your curve in a way that is parallel to the x-axis. So in the direction that is parallel to the x-axis. I hope you managed to grasp some notions. This formula clearly is just for, well, at one given point, AB. In general, we do it's exactly the same formula. I'm going to replace x by a by x, and b by y. Okay, I'm going to rewrite it. So in general, we have the formula to get the partial derivative with respect to x of a two-variable function. So in general, the partial derivative of f with respect to x at the point x, y, f of x, y is, well, as I said, I'm going to rewrite this, but I will put x and y instead. Do I erase my surface? is f(x) xy equal to limit as h approaches 0 of f of x plus h comma y minus f of xy over h. Now, as I said, I hope you grasp a little bit of the theory of the idea. If not, well, I guess what you really have to notice, again, this is my warning symbol, but I'm not sure it's a warning, it's more, I guess, what is really important. In all my story, I said the y value is fixed to b. So during my story, overall my story, I considered y as a constant, right? I fix it, that's b and that's it. I don't really talk about this anymore. I let x vary. So it's exactly what we have to do all the time. We have to, when we differentiate with respect to x, we have to view y just as a constant. That's what is important. So to find or to compute fx of xy, so the partial derivative with respect to x of f at a point xy, we thus treat or view y as a constant. And we differentiate f with respect to x in the usual way. But it means, okay, so I will give you expressions in x and y and ask you find a partial derivative of that function with respect to x. And now you know what to do. Maybe it will become clearer when I will show examples. But now you should know that y has to be seen as a number, as a constant. Which means that if at some point you have to differentiate y with respect to x, what do we get? What is the derivative of y with respect to x if y is viewed as a number? 0. So actually we're far from implicit differentiation. Don't mix the two concepts. Here, I guess I just erased my surface. But, okay, what is again dy over dx? It is the rate of change of y with respect to x. But here we have two independent variables, x and y. It's not because I change a quantity x that I have to change a quantity y. They are independent. So if I increase x by 1, y does not have to move. Okay, so that's why the slope is 0. In the implicit differentiation situation, it was really just one equation involving x and y, and if you change the x, if you still want the equation to hold true, you have to adjust the y. So y has to change for the equation to remain true. But here you don't have to, if you change x, you don't have to change y, because z will absorb the difference. Z will have to change, I guess, if you change x, but not necessarily y. There are two independent variables and that you use to compute the third one. Maybe a good time for a break. Examples to come. Digest that also. I know. You did it already?
Yeah.
Okay, it's about that. But
Yeah.
Yeah, I know.
It's a lot
easier than that last one.
You're right. The topic is different also. and- I was happy for you. You will have a relief and not too difficult assignment.
Yeah, but I remember there's assignment 6 or assignment 5, the numbers really complicated.
Maybe, but the numbers vary from one student to the other. So sometimes I've done different examples, and some students get easier numbers than the idea, the concept is the same, but it turns out that sometimes it's easier.
Someone got a number like billions.
Okay.
The result turns to be billions or millions.
Yeah,
or
okay.
A really huge number.
Okay. The concept is the same, however, but yeah, depending on the numbers you get.
Good time.
Okay, let's continue. I told you I would do example. Give me 5 minutes and then I will do examples. But maybe before I start the second half, there's something I wanted to tell you. If you read the course syllabus, it's mentioned that the worst assignment will be dropped for the assignment average, and I decided to drop the two worst, so it's going to help you a little bit. It might help a bit with the learning about web work. Yeah, so if you go on Moodle, the average that you see is already content. Well, the worst two are already dropped. Okay, so before the break, I explained, and by the way, the dropping is on individual basis, so it's really for each of you, your worst two are drops. It's not the worst two overall. Okay, so before the break, I explained how to compute the partial derivative with respect to x, but there is another variable into play, which is the y. So of course it's the same thing, so maybe a bit quicker. Similarly, at any point a, b, f of ab on the surface, one can study the slope in the direction parallel to the y-axis now. So study the slope in the direction that is parallel to the y-axis. So now you have your, maybe here, you have your surface. X, Y, Z. And you have a point, say here, which is your point A, B, F of AB. And now instead of fixing the y, you fix the x. So now you don't walk in the direction indicated by the x-axis because that would change your x. Now you walk in the direction indicated by the y-axis, so your x remains fixed. So you get a walk or a curve more like that, say. Okay? Depending on the mountains and valleys that you have on your surface. Okay? That's why it's not a straight line. It goes up and down a little bit. So now you can decide to walk in this direction instead, and then decide or find what the slope is. To the x-axis, that is when x is equal to a remains fixed. And y varies. So in that case, you get the equivalent of what we discussed before the break. So in this case, well, maybe I discussed the general situation, not just at one fixed point, but we have fy of xy is now the limit as h approaches 0 of f of, now x is fixed, but y varies, so x comma y plus h minus f of xy over h. Okay, so same story as before, but now it is y that varies and not x. So as you see here, x remains unchanged, constant from one point to the other, because these are points that we choose in the domain down here. But y varies, so
the y value is a bit different. So again, this is the height, if you want, or the z coordinate of 2 points on your curve. And so you compare the height over the distance between these 2 points. So you get the slope. So as I wrote for the partial derivative with respect to x, to compute the partial derivative with respect to y of a two-variable function, we now we view x as a number. So we consider, or we treat x as a number. And we differentiate f with respect to y now as usual with the same rules we have: product rule, quotient rule, power rule, and so on. And now if you have to differentiate x with respect to y, well, x is viewed as a number, is considered as a number, so it will be 0. Okay, same story as for the other variable. Okay, so I'm ready for examples, but maybe to summarize what we did, we have a surface, and if we differentiate with respect to x and plug the point AB in, actually we look in this direction. So if you differentiate with respect to x, you look in this direction, so the direction that is parallel to the x-axis. If you differentiate with respect to y, then you look in this direction, if you want, the direction which is parallel to the y-axis. So you are on a mountain, whatever where. You have two directions. You can look in the direction indicated by x, say this way. Is it going up, down? Is it steep? Or y-axis, is it going up or down? Okay, that's what we do. Okay, so you're standing up here at the top of offered, and then you look in the direction, and is it steep or not? Okay. Offered mountain, I guess. Okay, so let's see examples now. Okay, let's say we have f of xy. This is x cubed y plus x squared plus 3y minus 7. So a quantity that depends on two other quantities, x and y. And I will compute the partial derivatives. So let's say first, for fx of xy, so the partial derivative with respect to x, now I have to see y as a number, and the only variable I have is x. Okay? So what's the derivative of x cubed y in that case?
Okay, I wasn't sure.
Sorry?
Just 3x.
Almost. Okay, let me rewrite this. Normally, we don't write x cubed 2, right? We normally write 2x cubed, I presume. Okay? So y is a number. Okay, so let me just put it in front because it's a number. Okay, it's the same, exactly the same expression. Okay, I did not do much. But y is a number, like 2, right? How would you differentiate this if it was 2?
So it's just 3y squared.
You would drop the 3 in front, 3 times 2, x squared, right? It's exactly what we have to do here. Sorry, now equal is wrong because this is that. Sorry, I'm going to, Okay, let's drop that. It's easier this way. So I just erased the the x here because it was not equal. But now it's going to be equal. So I have fxxy. Because y is a number like 2, I would drop the 3 and get 6. So I have 3 times y. So I have 3y x squared. What's the derivative of x squared? 2x. What's the derivative of 3y? 0, because y is viewed as a number. Okay, like 2. 3 times 2 would be 6, say. Derivative of 6 would be 0. So plus 0, and of course the derivative of 7 is 0. Okay, so 3yx squared plus 2x would be, well, is the partial derivative of f with respect to x. Okay, so as I said, we're far from implicit differentiation. Here, x and y are two independent variables. So the derivative of y with respect to x is 0. How do we, well, what is now fyxy? So the partial derivative with respect to y of xy. Now, x is viewed as a number, and y is a variable. So what's the derivative of this first term? X cubed. Okay, x cubed. Well, if x is a number, x cubed is a number, right? So it is just a number times y. When we differentiate that, we just get the number. Like if I have to differentiate 2y with respect to y, it would be just 2. So here my x cubed is my number times y. So the derivative of that is just the number x cubed. So it is x cubed. The derivative of x squared? 0, because x is viewed as a number now. Derivative of 3y? 3, and the other one is clearly 0. So x cubed plus 3. Let's say I want to put numbers in. fx of 1, 2, for instance, means that I replace my x by 1 and my y by 2. Again, you have to pay attention to the order in which we list the variables. So if x takes the value 1 and y takes the value 2, in fxy, I replace x by 1, y by 2. I get 3 times 2 times 1 squared plus 2 times 1. That is then 6 plus 2, 8. And if I plug 1, 2 in fy, it means I replace x by 1 and y by 2, and there's no y. So just x by 1. So 1 cubed plus 3, 4. So again, it means that if you are standing on that surface here, and you're looking in the direction parallel to the x-axis, it goes up. The slope is 8. If you look in the direction that is indicated or parallel to the y-axis, then it goes up again, but it is less steep. The slope is just 4. Okay? Any questions on that? Let's do more examples. Strange sound. 2. Let's say I do f of x, y, which is square root xy e to the, I'm not going to take the same example. Let's say 2x plus y, like that. What is the partial derivative with respect to x? Yeah. What How do we differentiate this? How do I start? Product rule. Yeah, is that what you said? There's a product here, right? There's an expression in x and y, but I don't mind because y is a number. Maybe my bar is a bit too long. So there's an expression in x here times another expression in x. So I'm going to use the product rule. Now what's the derivative of this first term? Well, square root of xy is the same as xy to the power 1/2. So I drop the 1/2 in front. And I have to multiply by the chains, which means by the derivative of the inside, right? That's a chain rule, right? So you drop the 1/2 in front, you copy your expression, you subtract 1, and then times the derivative of the inside part, which is just y, because y is viewed as a number in that situation. My variable is x, all the other variable are numbers. So this is like x times 2 or 2 times x, so it would be just y. So this is the derivative of the square root xy with respect to x. I'm far from being done. Over. So the derivative of this part here times the second one. Maybe I will complete here because I run out of space. Plus the first expression times the derivative of the second expression. The derivative of e to the 2x plus y is e to the 2x plus y times the derivative of the power with respect to x, which is 2 plus 0, 2. Do I want to rewrite this? Not really, but okay, let's do that anyway. I've never done that before, I think, but I could put e to the 2x plus y in front. And here I get y over 2 square root xy plus 2 square root xy. You don't have to rewrite it, okay? I just decided to waste my time a bit. What is fyxy? I start with the same initial expression. It is again the product rule that I have to apply because y appears in both expressions. So actually here the role of x and y is almost the same. The only difference is that there is a 2 in front of x and no 2 in front of y. If it was just x plus y, I guess I could rewrite this exactly and swapping x and y, and then I would get the answer. But here again I drop the 1/2 in front. I subtract 1 times the derivative of the inside with respect to y now, viewing x as a number. So it is a number times x. So it is just x, the derivative of the inner part, times the second part, e to the 2x plus y, plus the first part, square root of xy, times the derivative of the second part, which is e to the 2x plus y, times the derivative of the exponent with respect to y. So 0 plus 1, just 1 I guess. And here again, if I want to rewrite, waste some seconds, I get 1 over 2 square root xy plus xy, square root of xy. Made a mistake, I forgot the x here. It goes there. So if you compare the two partial derivatives are quite similar. Let me not plug a point in because I don't have a calculator with me and I did not prepare this. So let's say 3 now. Third one I will create with you. Any proposal? You're missing the logs, I think. I think you're missing the logs. Okay, so let's say z is equal to 3x squared y plus ln of x squared plus 3y, for instance. I've been nice, I chose ln, which is easier to differentiate. By the way, I don't provide any formula sheet on the final exam, okay? So you have to practice and know your formulas. So maybe I can use a different notation. You see I wrote z this time and not f. So I can say, okay, what is then z index x, which replaces my f index x? Well, the y here must be seen as a number again. So I could rewrite this and write 3yx squared if I prefer to have all my numbers in front of my variables. So 3yx squared, and then if I differentiate with respect to x, I would drop the 2 in front. So I would get 3y times 2 x to the power 1. So I get 6yx or 6xy. Did I go too fast on this one? That's good. Plus, how do we differentiate the ln? It's 1 over what is inside the ln times the derivative of what is inside. Just 2x, because it's 2x plus 0. So if I want to rewrite it a little bit, I guess I could write 6xy plus 2x over x squared plus 3y. So that would be my zx. And zy, now 3x squared is viewed as a number, so I have a number times y, so the derivative is just a number, plus ln of an expression, 1 over the expression, times the derivative of that expression, 0 plus 3. So I get 3x squared plus 3 over x squared plus 3y. And here maybe I can plug some values here. Here I had an e to some power, so I was not able to compute it. But with a fraction, I should be able to make it. Say, for instance, zx, the point -1, 2, for instance, is, I replace x by -1, y by 2, so 6 times -1 times y. So my answer is here, at the top here. That's my zx. So I replace x by -1 and y by 2. Plus 2 times x, so 2 times -1 over x squared plus 3y. So -1 squared plus 3 times 2. Which is then -12 minus 2 over 7, which is what? This is 84, so -86 over 7. And correct me if I'm wrong, I think I'm right. zy. I replace x by -1, y by 2. So 3 times -1 squared plus 3 over x squared plus 3y. So -1 squared plus 3 times 2. So this is 3 plus 3 over 7. This is 21, so 24 over 7. Okay, so again, if you're standing on that surface, looking in the direction indicated by the x-axis, it goes down because it's negative. It goes down. The slope is -86 over 7. And if you rotate 90 degrees and you look in the direction indicated by the y-axis now, it goes up by 3 point something. Okay? That's good? Okay. No, not this now. This is the 2-variable situation. The 3-variable situation, 4-variable situation, it's exactly the same idea. It's just that I cannot draw 3-dimensional objects. So I guess it's harder to imagine I'm standing on that 3D, 4D object looking in a direction. That's a bit hard to imagine. So that's why I like to draw the surface, even if I'm bad at drawing surfaces. But so the idea is the same for the multivariable functions in general. So in general, if y is equal to f of x1, x2 up to xn, then y subscript xi, or if you prefer f subscript xi, is the partial derivative with respect to xi, is the partial derivative with respect to xi, and is computed by treating all the other variables, so all variables except the one you chose, xi, has constants, as numbers. Is computed by treating, let me list all the other variables, so x1, x2, up to x minus 1, jump over xi, so xi plus 1, up to xn as numbers, constants, computed by treating, and differentiating f or y with respect to xi in the usual way. Okay. Let me give a notation, and then I will do an example where there is more than just two variables x, y into play. Notation. Suppose that y is equal to f of x1, x2, xn. then I can, okay, then, because you certainly remember that in the one variable situation we had the prime, f prime notation, but we also had the d. So I just want to show you how we use the d notation here. So I can write, say, f xi, or I can write, it's a d, but it's, I don't know why, it's a fancy d when we perform a partial derivative. So it's a fancy d like this. Like this. Or I could just write fancy d y over fancy d xi. Okay? Yeah, okay. And if I want to assign a certain value, I could say, okay, f xi. Let's say I want to assign values to my variables. So at the point a1, a2, up to an, if I want to use the d notation, the fancy d, I can say, okay, this is going to be fancy d of f, and then we had a vertical bar, and we put the n tuple. So maybe here x1 is equal to a1, x2 is equal to a2, up to xn is equal to an. Okay, this is just notation, and the same with the y. Okay, so roughly it is the same notation as usual, but there is a fancy d. So let's see an example. Any questions on that? The notation? It's roughly the same as before, okay? Example. If y is equal to x1 squared times x2 over x3 plus 7 times x4 square root x1, then I will compute the derivatives with respect to the four variables we have, x1 up to x4. Using the fancy d. What do we get? Zero?
The first part is 0.
Well, x1 is there. Huh? X1 is there, so it should not be 0. Yeah? I could use the quotient rule if I want, but in my opinion, it's a waste of time. x2, x3 are numbers, like 2/3, I don't know, okay? So that's a number, right? So you can write, maybe if I want to rewrite this, I could write, this is the number x2 over x3 times x1 squared, right? It's exactly the same thing. So x2, x3 being numbers in that situation, you just drop the 2 in front, x1. So you get 2 times x2 over x3 times x1. So 2 x1, x2 over x3 if I want to keep the same order as before, but it's just the same thing, okay? That's good? For the first part. Yeah, I'm not done. Second part. This is, of course, the same as x1 to the power 1/2. So I can take the 1/2 and drop it in front. So 7x4 times 1/2. So it is 7x4 over 2 times x to 1 to the negative 1/2. Or if I don't like the negative exponents, I could say 7x4 over 2 square root x1. Everything that is not an x1 is considered as a number. Okay? So x2 was considered as a number, x3 was considered as a number, x4 also. My only variable is x1. Now, partial derivative of y with respect to x2. Now, everybody except x2 is viewed as a number. So maybe it's not the best way now to rewrite this expression. Maybe the best way is just as it is, I presume, because the x2 is, well, the last variable in the list. So my x1 squared over x3 can be viewed as a number that multiplies x2, right? It's exactly the same thing. So the derivative of this expression with respect to x2 is a number times x2, so the derivative is just the number. So x1 squared over x3. And what's the derivative of the second part? Now 0. There's no x2 there. Okay? You can do the product rule and waste your time and do 0 times 0, 0 times square root x1 plus 0. Anyway, 0. So plus 0. Partial derivatives. With respect to x3. I guess I don't have to rewrite it, maybe just keep it as it is. It's a number over x cubed, x3, not x cubed, x3. It's not this, completely different. So I can do the product rule, or the quotient rule, or I can move this guy up with a negative exponent and drop the negative exponent in front and subtract 1, okay? So that's always my way of viewing it when the denominator is so simple. I prefer to move it up. So I have x3 to the negative 1, and I drop the negative, so I have negative 1 times that, x to the negative 2 that I can drop down after, or I apply the quotient rule, so the derivative of the numerator, which is 0 times x3, so 0, minus the numerator times the derivative of the denominator, which is 1, over the denominator squared. So we just get, at the end, minus the numerator times the denominator squared. And for the last, the second term, derivative of that? 0, there's no x3. And partial derivative with respect to x4. Derivative of the first expression is 0 because there is no x4. And the derivative of the second part, the 7 together with the square root x1, this is just a number, right? So I could rewrite this expression as 7 square root x1 times x4. So it's really the number 7 square root x1 times x4. If I differentiate this, number times a variable, you just get the number. So plus 7 square root x1. Okay? This is what your new assignment is all about. Partial derivatives. Okay? Maybe one more example. 2. If P is R S U over R plus T, so P depends on R, S, T, and U. Again, there are 4 variables. Then the partial derivative of P with respect to R, say. Now I need to use the quotient rule because R appears at the numerator and denominator. So it is the derivative of the numerator, which is SU times the denominator, R plus T, minus the numerator times the derivative of the denominator, 1 plus 0, so 1 over denominator squared. Let's say I want to plug a point in, let's say in particular, if I plug the point, R takes the value 1, S takes the value 2, T takes value 3, say, and U takes the value 4, for instance, I just plug in. So S is 2, I said, U is 4, so this part is now 8. R plus T, this is 1 plus 3, 4. Minus R times S times U, so 1 times 2 times 4, 8 times 1 over R plus T squared, so 4 squared, which is 16. So 32 minus 20 minus 8, 24 over 16, 3 over 2. Yeah? Okay. Do I have to differentiate P with respect to the other variables, or? I don't mind, I can do it, I have time. I do it? Or? No, it's fine? Okay. This is where the material for your new assignment ends, so that's why I had time. 35 minutes, 35 minutes left. Okay, so you can practice. I didn't say the course was over there. Okay, so if I have time to speak about something else, I will. Um, 17, sorry, 17.1. 17.2 now. Applications of partial derivatives. Not quite sure you will like the applications. It's not really real life applications, I guess. It will be more, well, yes and no, but it will be more in terms of estimations, approximation. Okay, so first, approximation. When I was a student, I was always disappointed. The word application wasn't the board, and I was excited, and afterwards, no, that's not really an application. It's not a real life application, but okay. Now it's my turn to disappoint you, I guess. So, approximation. Should I do a reminder here? Maybe. Maybe I start with a reminder in a one variable situation. Okay, let's say let y is equal to f of x. So my reminder is, if you remember, I defined how to compute f prime, and then we use f prime for approximation. So the discussion we had was, okay, you have the x-axis, the y-axis. So I'm in the one variable case here, and then you have a curve, say, and then I told you, okay, you can choose, say, a value, an x value, say a, and compute f prime a, and f prime a turns out to be the slope of the tangent line at that point. I'm a bit too close to the end of my axis. We need more space. So, okay, so if I draw the tangent line, something like that, say, so that's the tangent line, whose slope is f prime a. And I said, okay, now if I increase my a little bit, or my x value a little bit, let's say I have, I think I use delta x. It was probably just x and delta x, and x plus delta x. Okay, so if I increase my x value a little bit, whoa, this is supposed to be vertical, then I have this point here and this point there. I have 2 points, one on the curve, the other one on the tangent line. And I told you, okay, this here, what is this? Well, if f prime a is the slope, and what is the slope again? It is the variation along the y-axis when x increases by 1. So if x increases by delta x, then this is the slope f prime a times the increment, times the augmentation. And from here to there, this part here, from that point to that point, actually I am comparing the y values of these 2 points, because clearly these two have the same y value. So I'm comparing the y values of these two. This is f of a plus delta x minus f of a. And then I said, okay, here maybe I'm far, so this is not really close from that. But if I'm pretty close to that point, if I'm just here instead, then the tangent line will be super close from the curve, so it will be a good approximation. So what I told you some weeks ago, I guess, was that f prime a delta x is an approximation of f of a plus delta x minus f of a. And we apply this to one specific value of delta x, which was 1. So in particular, if delta x is 1, then f prime of a is an approximation of f a plus 1 minus f a. Yeah? Do you remember that? You had to apply it in one of the assignments. Okay? That's what we used before. And now we're not in the one variable situation, but in the several variable situation. But the idea is exactly the same, because when I told you if we want to compute the partial derivative, we have to treat the other variables as constant, which means they don't move, they're fixed. And then we can augment or, well, increase or decrease the variable that we use for the derivative. So I can decide to fix all the variables except one, and I let this variable, say, increase by 1. And then if I have several variables, and I can compute f of the point where only one variable has been increased minus f of, say, my starting point. It will give us variation in the height or in z, And then I can, again, estimate it with the partial derivative. So let me write it down. I guess it's, okay, I'm going to write it for the two variable situation, but it's true, this is true for the n variable situation as well. So, okay, f, let's say we have z, which is f of xy. As I said, I could write several variables, okay? It works in the more general setting. Then, fancy z over fancy, fancy d z over fancy dx, the partial derivative of z with respect to x is, well, I guess I can write also fxy, and it is the rate of change of z or f, let's say z, with respect to x when y is held fixed, because we consider it as a constant, as a number. And similarly for y. So if I compute the partial derivative of z with respect to y, I get exactly the same thing here, but I replace x by y and y by x. So the partial derivative of z with respect to y that I can write as this fy xy, this is the rate of change. Again, I should write the instantaneous rate of change, but we never write it. So of z with respect to y when x is held fixed. And now you have to imagine this situation, but now with a surface. I'm not going to draw it. But you have a surface, you have a point xy, well, xy, f of xy on your surface. You say fix y, and you walk along the direction indicated by the x-axis. And then again, actually it's not a tangent line that we have, but we can define, and I'm not going to do it, but we can define a tangent plane. And then you walk on the tangent plane in the direction indicated by the x-axis, and then you can compare the variation estimated by your tangent plane with the actual variation walking on the surface. Okay, it's exactly the same idea. So, just as in the one variable case, actually, this reminder is, well, is not, but is in section 2.3. So we can say that f of fxab is an estimation of, well, my variable is x, y is held fixed. So if I increment, and I'm going to jump here right away, but actually it's the same story. I could have a delta x and write a more general, maybe I do it. The more general formula would be, if I let my x vary a little bit, then I have this times delta x, and it would be the same thing as over there. So it would be f of a plus delta x y minus f, not yb, sorry, y is b, fab. And in particular, when delta x is 1, we get that the derivative, the partial derivative with respect to x, you plug a point in, and this is an approximation, an estimation of f of a plus 1, comma b, minus f of ab. You see, it's the same formula as there. as I said, it's not a tangent line anymore, it's a tangent plane. You walk on the tangent plane, it approximates the surface if you're close to the point, and this is actually the variation that is, well, this is the approximation of the variation when you walk on the tangent plane. On the right hand side you have the exact variation, but you still have an estimation. And of course it works for y as well, so fyab, say delta y is an estimation of f of a comma b plus delta y minus f of ab, and in particular if delta y is 1, you get this. Okay? Maybe a remark that I could have made in the one variable case, but I never did it. What do I get if, say, delta x is negative 1? If delta x is negative 1, then I get negative 1 times fxab. So negative fxab is an estimation of f of a minus 1 comma b minus f of ab. And I can rewrite this. I mean, if I just multiply by negative 1 on both sides, I get f of xab is an estimation of f of ab minus f of a minus 1b. So actually we can not just estimate what happens when f increases by 1, but also what happens when x decreases by 1. Okay? And it's the same in the one variable situation. Instead of moving, increasing x, I could decrease x and have the same observation. Honestly, I did not put examples, or I should say problems in the assignment with estimations because I wasn't sure I would have time to discuss it. And I guess I have to verify it for the next assignment because I will put some questions like that on the assignment. But I'm pretty sure that you will have to use this and not this, because pay attention actually, because if I want to approximate this, I can also compute fx of a minus 1b. So you have two different values, two different points that approximate the same thing. Because you can approximate an increase here or a decrease. So so this guy approximates two different things, or you can use two different points to approximate the same quantity. But normally it is this formula. So actually I will make sure that the questions that I choose, you will have to use these two, okay? So I will try to avoid that just because I want the questions, or I want for you to be, well, I want you to know exactly what you have to do. Okay, examples. The cost function, I did not write it for y, but of course it works also for delta y. It's the same idea. The cost function of a manufacturer is C, and my two variables are QA and QB. So quantity of product A and quantity of product B. So it's given by ln QA plus 3QB over QA plus 2QAQB. Where QA is the number of units of product A, or say just type A, and QB is the number of units of type B. And the question is, compute CQA of 410 and CQB of 410 also, and interpret the results. Interpret in the sense of approximation. Okay. I will use a little trick, actually. Not that I have to, but I think it's a good idea. Because, of course, I would have to differentiate this partially with respect to QA and with respect to QB. That's what I am asked to do, which means I will have to differentiate this ln. And I guess it's possible. I mean, it's 1 over what is inside the ln times the derivative of, so 1 over what is inside times the derivative of what is inside. There will be a quotient rule, and there is a way to avoid that quotient rule. So maybe observe first that, well, I think it's going to simplify our task a little bit. I can rewrite my cost function in order to avoid the quotient rule. How can I do that? Is it the magic one? No. It's ln. It's ln of a quotient, right? What is ln of a quotient?
Ln of the top number minus ln of the bottom.
Exactly. So I think it is a bit easier. Not that we have to, but I think it will be easier if I rewrite my cost function as, well, with 2 lns instead of 1. Again, this is really optional, not something you have to do, but I think it helps here. So minus ln of the denominator, which is just QA, plus 2QA QB. Okay? So if I have to differentiate it with respect to QA, now QA is the variable, QB is a number. Of course, you have to apply the log rule. The log rule is 1 over what is inside, QA plus 3QB, times the derivative of what is inside. The variable is QA. QB is viewed as a number. So 1 plus 0, so just 1. Minus the derivative of ln QA, 1 over QA, times the derivative with respect to QA of the denominator, of QA, which is 1, again. And what's the derivative of 2QA QB? 2QB. Good. So if I rewrite this, I get 1 over QA plus 3QB minus 1 over QA plus 2QB. Now, if I plug the point 410 in, so CQA of 410, I replace QA by 4 and QB by 10, I get 1 over 4 plus 3 times 10, so 30, minus 1 over 4 plus 2 times 10, so 20, and I got 19.78. And my interpretation would be, because I have to interpret the result in terms of approximations, maybe I just erased what I needed. Okay, how can I use this as an interpretation? When we differentiate with respect to the first variable and we plug a value in, this is an estimation of C510 minus C410. Okay, that's what we put on the board. So the extra cost, I'm going to write it C510 minus C410, let's say, to produce 5 units of type A instead of 4 when the production for units of type B is held fixed at 10. Is approximately $19.78. Okay, that's what our calculations indicate. Yes?
Where'd you get 510 from? It's just like you automatically go down one, or it's just or did it say that somewhere?
Yeah, so what I put on the board was this is an estimation of f of a plus 1 b minus f of ab. Okay, so I just used that actually. Okay, so CQA of 410, this is an estimation of C4 plus 1, so 5, 10 minus C of 410. Okay, it was on the board some minutes ago. Okay? Of course, I don't need to go through all this to get, actually this is just an estimation and it's not the exact answer. To get the exact answer, I mean, I just plug 510 and 410. So I compute C of 510, I compute the number, minus C of 410, I compute the number. Okay, so I'm not telling you that this is more efficient than plugging numbers in. It's not what I'm telling you. I'm telling you that this is just an approximation, and sometimes we just know the rate of change of something without really knowing the function itself. So then we could use the rate of change to estimate. And I said that this is an approximation just for, well, by curiosity, I computed the exact value. So the exact value of this, C510 minus C410, this is exactly $19.81. So you see in this example, we're quite close. And I want to do the same with QB. So CQB of QA QB is the derivative of my c, which is still here, with respect to qb. So it's 1 over what is inside the ln, qa plus 3qb, times the derivative of what is inside the ln with respect to qb. Now my variable is qb, my qa is viewed as a number, so the derivative is 0 plus 3, so 3, minus the derivative of ln qa. qa is viewed as a number now, so ln qa is a number, its derivative is 0, and plus 2qa, because qa is viewed as a number, so it's like a number times qb. So plus 2qa. So this is 3 over qa plus 3qb plus 2qa. And again, if I play the same game and plug 410 in, so I get 3 over 4 plus 3 times 10, 30, plus 20, and I got 8.09. Well, I had to round up a bit. It's roughly this.
What, 20?
It's, thank you.
Yeah, 2 times 8.
Thank you. It's 2 times 4, 8. Makes more sense. Thank you. And now if I want to interpret this result, now I differentiate it with respect to the second variable. So this is an approximation of the variation in the cost when we produce one more unit of type B now. So the interpretation would be the extra cost C for 11 minus C for 10. So this is really the extra cost because my C was the total cost. So total cost to produce these 15 units minus total cost to produce these 14 units. So it's really the extra cost is to produce 11 units of type B instead of 10, when the production level for type A is held fixed at 4. Is approximately well, we found $8.09. And again, I computed the actual variation. So C for 11 minus C for 10. If you take the time to replace, well, now my function is gone, but to replace QA by 4, QB by 11, compute the total cost and subtract this one, I got $8.08. Maybe the numbers are well chosen, our approximations are pretty good. It's not always as good as in this example. Questions? So as I said, there was no question about that in the assignment, but there will be in the next one. And I guess I'm done for today.